What's up, everybody? It is Mr. Prevet here to do some more calculus with you. Today, we're going to be looking at the 2024 FRQ number 1. As we know, on the AP Calculus exam, questions 1 and 2 are calculator questions. So we're going to be bringing out the calculator. Hopefully, I put it in a spot where you can see what I'm doing on the calculator, but also see some written work. I'm going to try and do my best with it. But I'm excited to jump into this question. So what I'm thinking is I'll put the calculator here on this side. Hopefully you can see it just fine. And I'll put my work over here on the right. So here we go. Question 1. It says the temperature of coffee in a cup at t minutes is modeled by a decreasing differentiable function, C, where C of t is measured in degrees Celsius. For t is between 0 and 12, selected values C of t are given in the table shown. So they give us a table of t and C of t. Great. Part A says approximate C prime of t using the average rate of change over the time interval. So I'll write down C prime of 5. And we're using t over the interval 3 to 7. Show the work that leads to your answer and include units of measure. So a great approximation for an instantaneous rate of change, like C prime of 5, is an average rate of change, which is what they're asking us to solve for. And our average rate of change over this interval would be C over 7 minus C of 3 divided by 7 minus 3. Looking at our table that they give us, we get 69, nice, minus 85 divided by 4. Now, we could use our calculator, there wouldn't really be a need. We're all smart folks. We would get an answer of -4, but the question specifically asks to include units of measure. We know that C prime of t is the derivative of C with respect to time. So this is going to be whatever our units of C are divided by our unit of time, which in this case is degrees Celsius per minute. So that would be our unit of measurement. And this makes sense, right? C prime should be how fast our temperature is changing at a given point. So that is part A, relatively simple, super quick. But now we're going to move on to part B. So part B is talking about a Riemann sum. It asks us to use a left Riemann sum. So part B, it says use a left Riemann sum with the 3 subintervals indicated by the data in the table to approximate the value of the integral from 0 to 12 of C of t dt. Interpret the meaning of 1/12 of this value in the context of the problem. Okay, so they're first asking us to solve this integral, which is we're going to do using a Riemann sum, and then interpret 1/12 of that integral later on. So let's start at the beginning. Let's think through a Riemann sum. We know that for a Riemann sum, we are going to sum up all of the lengths of our interval times the value of the function at one of the endpoints or the midpoint potentially. In this case, they're asking us to do a left Riemann sum, so I'm going to use the leftmost value. So the first interval is from 3 to 0, so that is a length of 3, and I'm going to use the left value, which is 100, or C of 0. The second interval has a length of 4. We'll use the value 85. And then my final one has a length of 5. I'll use the value of 69. Plugging that into my calculator, which hopefully will get me the right answer. 5 times 69. Plug it in. Boom. I get that is equal to 985. Now, this is just an integral, right, of a function. We don't really have a way to integrate degrees Celsius. That feels really weird, but the question specifically asks us to interpret the meaning of 1/12 times the integral from 0 to 12 of c of t dt. And they want us to interpret this. Now, we know that the integral from a to b of a function divided by the length of that interval, or b minus a, which is 12 minus 0, this is the average value of c of t on the interval 0 to 12. And this is something that's really important, understanding that the integral from a to b of f of x divided by b minus a, that is the average value of the function. So it is the average value of c of t. You could also say it is the average temperature of the coffee in the cup over this interval from 0 to 12. However you put it, as long as you say it's the average value of c of t, I think you should be all right. But hopefully that makes sense, testing our Riemann sums and our understanding of average value. But so far, part A and B haven't really been super difficult in terms of the actual calculator skills, right? So far, we've just been using it as essentially a 4-function calculator. So hopefully one of these parts coming up, tests us in terms of our calculator skills. Because calculator skills are great, right? We don't actually have to know how to do calculus. The calculator does it for us. But we'll see if part C and part D kind of help us do that. So, part C. For T is between 12 and 20, the rate of change of the temperature of the coffee is modeled by, I'll write it down. It's pretty ugly, but C prime of T is equal to negative 24.55 e to the 0.01 t divided by t. So that's our rate of change of the coffee, or the temperature of the coffee, sorry, where C prime of t is measured in degrees Celsius per minute. Find the temperature of the coffee at time t equals 20 and show the setups for your calculations. So we have this rate of change function for t is between 12 and 20. I'll have to replace my Sharpie soon. But one thing that we also know based on the table is that my temperature at t is equal to 12 is equal to 55. One of the fantastic things we learned about accumulation functions, that if I want to find, in this case, I'm looking for C of 20, right? Because we want the temperature of the coffee, 20. This is going to be equal to our initial value plus the integral over our interval, which is 12 to 20, C prime of t dt. Because when we integrate a rate of change function, we will get an accumulation of change, in this case from t equals 12 to t equals 20. So if I take that accumulation of change and add it to my initial value, I should get my final value. So we can now plug this in. So C of 12 we know is equal to 55. So I'll type that in. It's nice and easy, right? But now we have to solve this integral. And there are a couple of ways that we can solve integrals, but my favorite way is by going to the math section, going down to number 9, and it should say function int, right? And that represents a definite integral. And it's great. I can just plug in these values. So my t is going from 12 to 20. Now, I personally just do everything in terms of x, so I'm not going to use t like the question does, but I'm going to plug in my c prime of t just in terms of x. It'll work out the same using the different variable. But 24.55, you can do second ln to get e to the 0.01 x, all divided by x. And this should give me, if I put in my dx as I should, I click enter, and this gives me my temperature. So I'm not exactly sure what the value of this is. I mean, we could calculate it by doing this minus 55. But this final temperature should be 40.329. And this will be degrees Celsius, right? Because all of our coffee temperatures have been in degrees Celsius. And this logically makes sense, right? Over time, our coffee should be getting colder. It is in the table. So when we integrate our function from 12 to 20, this integral should give us a negative value because our temperature should be getting more and more negative, thus making our temperature at t equals 20 a little bit smaller than 55. But that would be our correct answer for part C of number 1. But that's all we got for that one. So we're going to move on to part D, our final part. I think part A and part B were relatively quick questions. Part C and D, I think, might take up more of our time if I had to guess. But let's look at it together. So part D, it says for the model defined in part C, it can be shown that our second derivative, C with respect to time, is something even uglier. It's 0.2455 e to the 0.01 t times 100 minus t. Gosh, I'm losing room because it's so big. Divided by t squared. And it says that this is our second derivative. And it asks us over the interval 12 to 20 to determine whether the temperature of the coffee is changing at a decreasing rate or at an increasing rate. So our very first thing is we need to interpret what this question is asking us for. It says determine whether the temperature of the coffee is changing. Okay, so that's talking about our derivative, right? At a decreasing rate or an increasing rate. So that's asking us, is our derivative increasing or decreasing? Or asking if our first derivative is greater than 0 or less than 0. We're just trying to figure out where is it positive, where is it negative. So we can go to our handy dandy calculator to figure this out. And the way that I would try and approach this is by saying that by going to my calculator, typing in my second derivative, which in this case is a little bit ugly, so we're going to need to be careful to not make a mistake, okay? Then I'm going to multiply it by 100 minus x, and then divide it by x squared. And I'm going to graph it. My window's all sorts of messed up, so I'm going to go to Window. I'm going to make my maximum x value 12, my minimum x value 12, my maximum x value 20. So now when I click graph, I get basically just a straight line across. So in order to fix this, I'm going to click the zoom button and go down to zoom fit. And this is an awesome thing that should make it really clear where our function is. Now we're trying to see where is it positive, where is it negative. If we go all the way down kind of to this final value, we see that we're positive this entire time. Even if I made my minimum y value like -1 so we could see it better, our y value is never crossing 0. Our function is always positive. So therefore, our second derivative is always positive. So therefore, the temperature of the coffee is changing at an increasing rate. because our second derivative is greater than 0. So this question winds up really nicely. We don't have to check for any intersection values to split it up into separate subintervals because it's positive the entire time, giving us the answer for part D. So that's all we got for question number 1 on the 2024. And I hope that this was helpful. And yeah, happy practicing, guys. And I'll see you in the next video.